Okay, I think it's about time that we start today's webinar. So first of all, a warm welcome to everyone who joined. My name is Niels Verdijk, and I will be your host today. Apart from being your host, I'm also one of the customer support engineers at Diabatix. So basically that means if you have any questions or if you have any technical issues, you will for sure get in contact with me again. But that's enough about myself. Let's move on to the to the interesting stuff, which is of course today's topic, ColdStream Nxt for Powertrains. ColdStream Nxt, of course, being the latest release, the latest version of ColdStream, where we will look at the main benefits of that release and apply it then to the design of powertrains, or the cooling for powertrain applications. For today, I'll of course give a brief introduction both to Diabatix and to today's topic. Then I'll handle heat management in electric motors a bit more in detail before jumping into the case study itself. If you have any questions, feel free to put them in the chat box. Moderators are following along, so if they will answer your questions already beforehand. Any interesting questions or any open questions I will cover towards the end of the webinar. And lastly, if you see something interesting, if you see something useful for yourself, I'll give you some information about how to access ColdStream for yourself. And as ever, I'll try to keep this within that 30-minute mark. Starting with the beginning, what is Diabatix? I do see a few new names. So for those who don't know Diabatix, we are in essence a software company, and our main driving force, or our main vision, is that we believe smart algorithms should empower engineers to design beyond human imagination. What do we mean by that? Our software gives you the access to very smart algorithms, and that are able to boost your progress, both performance-wise as well as output-wise. So basically to enhance your capabilities as a thermal engineer. On the top right you see two very big names within the CFD world, ANSYS and Hexagon. They acknowledge the strength of our software, have reached out to us, and I won't say as of recent anymore, because we have been partners for quite some time now, but we made them our technology partners. But that's enough about Diabatix. Let's jump into heat management of electric motors. So first of all, why should you care? As you know, heat, or any component within an electric powertrain, produces heat. The electricity, through the components, or the components themselves, have a resistivity. So when electricity passes through it, it generates heat. When the heat up is so significant, that will result in failure of the component, or at best throttling of the component. So it's something very important, and usually it's tackled towards the end of designing. So where system engineers, or where engineers in general, mainly focus on the application first of the electric motor or the powertrain in general, and later on tackle the thermal problems, which is not the most efficient way of tackling, if you ask me. So that's where we come in, or that's where we see our biggest strength. By using the generative design capabilities of ColdStream, you can bring that thermal, or you can tackle that thermal problem much more early in the design cycle, giving you very quick feedback on what is feasible and what not. What is the impact, or what are the main benefits? By tackling the thermal problem early on, you reduce the amount of engineering work that you have to provide, as well as ColdStream will do some of the heavy lifting, and it will enhance the motor performance. Because usually, if you tackle the thermal problem, towards the end, it's a bit limited to what you can do, because usually everything else is more or less fixed. But if you tackle it early on, throughout the layout, for example, of the electric motor, you enhance, or you give the thermal problem, or you tackle the thermal problem in a much more efficient way, resulting in better temperatures, and thus also better performance of the electric motor. I hope I convinced you. Let's then move on to how ColdStream actually works, or what the main benefit is of ColdStream Nxt. On the left, you have the conventional way of tackling a problem. So as I mentioned, usually it's towards the end where your entire heat map is laid out, and you then have some space that you allow for cooling. What do you do first? You create a CAD model based on your previous knowledge or on heat sinks that work best. You do receive simulation, or you perform experimental validation, or you just rely on correlations. You post-process the results, you analyze the results, and then you cycle through this until you get a solution. As you can imagine, it's quite intensive, or quite a lot of manual effort needs to be taken to complete this cycle. With ColdStream, we linearize this problem. So we start again from the same. So you have a given layout and a given space for cooling, and then by using ColdStream, you can immediately jump into the quick concept generation. That's where ColdStream Nxt came in, by allowing or giving you as a user access to more conventional cooling structures like pins, fins, and giving those results in a very quick manner. You can get great insight into what design change affects performance, as well as whether or not your thermal requirements are met with a given layout. So that's this stage, the concept generation stage. It might be that one of those is already sufficient. If not, then you can of course continue to the detailed design generation. That's something that we covered earlier in a lot in previous webinars, so I won't delve into that too much anymore. But then you can get something very interesting, very intricate, like the example that you see below. But usually, or in a lot of scenarios, that's not needed. In a lot of scenarios, the concept generation, so the more conventional cooling structures like pins and fins, that is sufficient. And by giving you as a user that information early on and very quickly, that dramatically reduces the amount of efforts you have to put into it. Yeah, so as I mentioned, it's for today's webinar, we'll mainly talk about the concept generation stage, where you get a lot of data points for you to analyze and for you to basically to help you see what a design change affects the performance. Okay, you might think it's quite difficult to work with. Not at all. This slide deck highlights what steps you need to take. First of all, you upload a CAD geometry, of course. ColdStream itself is not a CAD environment. Everything needs to be prepared beforehand. So your chip layout, your housing, etc., all of that needs to be prepared beforehand. You simply upload it to the platform using a step file. You set the solids and the fluids. For example, your chips are made out of copper, your housing is made out of aluminum. Inside of it, it's air cooled or liquid cooled, and if it's liquid cooled, you can specify whether it's water glycol, or something else. So that's something that you specify here. Next, you set the boundary conditions. So, for example, how much heat do the chips produce? What is the inlet condition? Do you want to consider a fixed flow rate inlet, where you specify, for example, a given velocity, or do you want to specify a given fan or pump at the inlet or outlet? That's something that I'll leave it to you. For electric motors, what is something rotating? So that's all the information that you provide here by basically defining the problem statement. Next, you set the targets. So that lets ColdStream know what to optimize for, be it maximize heat exchange efficiency, minimize the weight, or if you have any flow problems, you can maximize or minimize the viscous losses. That's something that I'll leave up to you. What makes the most sense for this case, of course, you want to maximize heat exchange efficiency. And lastly, within the concept generation stage, you of course have to let ColdStream know what kind of concepts can be considered. Or pins and fins are your sole option, or can you allow for TPMS structures like gyroids, or lidenoids, or Schwartz elements? That's the last thing that you give ColdStream. Once all those options, once all that input has been provided, You simply click on the submit window, and ColdStream will do the work for you. All of this, if you're somewhat familiar with ColdStream, should take at most 5 minutes. I will discuss these steps in more detail when we get to the demonstrations session of the demonstration part of this webinar. Okay, so of course, as a user, you can dictate, or you have control over how those structures can be manufactured. For example, if you consider pins or fins, you can consider them being CNC milled or die casted or 3D printed, of course. For each of those manufacturing techniques, you have control over the settings that govern that technique. For example, if you have a look at CNC milling here on the left, if you look at planar CNC, the leftmost picture, you have control over the milling tool size, so basically what is the minimal channel width, as well as the minimal structure width, to make sure that the component is structurally sound. If you have a look at die casting, the settings are quite similar, so you can have a minimal channel width and a minimal feature width, but you now also have control over the release angle to easily get it out of the mold, and the fillet radii at the tip here and at the root. And for 3D printing, you of course have control over the RF min, what do you call the RF min, the minimal feature size, the minimal printing resolution, as well as the overhang angle and the unsupported lengths, both cantilever and bridge. Sheet metal forming is also an option, but not for pins and fins, so I will skip this part as it's not really applicable in the powertrain environment. Okay, that's the main introduction to ColdStream. Now we can move on to the actual case study, and that's to cool the electronics box, basically the electronic control unit that controls the electric motor. So our main heat sources, our main cooling structures will be made out of copper. In total, we have 70 watts of energy that we have to distribute, that have to evacuate, distributed over 3 heat sources, so 3 chips. As I mentioned, we want to maximize heat exchange efficiency, so we will use a temperature minimization objective, and we allow for both TPMS structures like gyroids, Schwartz elements, split piece, as well as pins and fins. Manufacturing, I put a question mark there. TPMS structures will of course be 3D printed. Pins and fins, I will leave up to you if you want to 3D print them, or if you want to CNC mill them or die cast them. Okay, let's move on to ColdStream itself. Let me switch my screen here. Yes, you should still be able to see my screen. Yeah, perfect. This is ColdStream, or at least the main landing page after you log on to the software, and that's the project overview. As the name implies, it gives an overview of all your different projects to keep everything nice and tidy. So let me scroll down to our electronic box. Yes, and inside of your project folder, you then have your different cases, the engineering problems that you want to solve. ColdStream supports 3 types of cases: standard design, custom design, and simulation. Although simulation is not present in this view. So a simulation is a regular CFD simulation. If you have a design, or if you just want to do a CFD simulation of what we call the empty design, so without any cooling structures, you can easily do so. Very comparable to other CFD tools like Ansys Fluent, Cradle CFD. Next we have standard designs. That's the concept generation, where we will focus on where ColdStream will design something for you, but what it can design is the cooling, the heatsink solution is limited. As a user, you dictate what ColdStream can consider. And lastly, we have then the custom design, the full-fledged topology optimization, and that's really to extract the maximum out of it. If no concept can be made, or if no concepts exist that can meet your thermal requirements, only then would you consider a custom design. But as I mentioned earlier, standard designs may be already sufficient for you. Okay, so once you create a new case, of course you'll have to upload a step file I will skip that part and go straight to a case that already has a step file. Simply clicking on step file and waiting for it to populate. It's not as interesting. So I'll go straight here, show others, yes, yes, and yes. Perfect. So here in the GUI in the middle, we have an overview of our geometry, and on the regions tree on the left, we have all the entities that are predefined in my CAD environment. So even the air has to be prepared early on in the, or has to be prepared in my CAD environment. It's basically a simple Boolean cut operation, or simple Boolean cut operation of the negative space. And the only thing for me then to do is to click on each of the entities and fill in the information. So starting with chip 2, that's the green volume here on the top right now. On the right hand side, ColdStream will now ask me what kind of entity is this? Is it a solid or a fluid? In our case, of course, it is a solid. I can change the name if I want to, and then I'll let ColdStream know what kind of material, out of what kind of material it is made. I of course have used copper, but if you want to use aluminum 6061, you can easily change that a bit. Yes, you can easily search for it and select an aluminum if applicable. And that is sufficient. So once you provide the material property, that is enough. Everything below is optional. If your material allows for it, you can enable radiation. For example, if it's transparent, then it makes sense to do so. You can also add a volumetric heat source, which of course in this example is applicable. So in this example, the chip, the green volume, in total produces 10 watts of energy. And for electric motor, it would of course make sense to add rotation, for example for the rotor part, to make sure that they spin. Which of course in this example is not the case, so I will leave that blank. Okay, so that's it for chip 2. You can then repeat that part for chip 1 and for chip 3. Fill in the material and fill in the heat source. And same for the cover, a solid made of aluminum, a housing, a solid made out of aluminum, and then our main PCB, which we will just assume as not producing heat, that we ignore any heat production by the rest of the components. As I mentioned, we then have the negative space being filled by air, and here of course it's a liquid, so we will, it's a fluid, so we will now select type fluid, and again you specify what kind of fluid is used. Is it air, is it water glycol, or something else? In our case it is regular air, so I will select this one. Perfect. And that's again sufficient. Everything else is optional. For example, if two-phase cooling is applicable, you can enable boiling. If natural convection is applicable, like it is in this example, I will enable it. I will set the environmental conditions, so our reference pressure is at 1 atmosphere, and our reference temperature is at room temperature, so 20 degrees Celsius. And lastly, I have to specify in what direction the gravitational vector points. I expect my component to be oriented like this, so the gravity will act in the negative, along the negative yellow arrow, and the yellow arrow is the y-axis, so here I specify -y. I can change the turbulence model if I want to. I can change it from laminar to k-omega SST and everything in between, but I will leave it to the default k-omega SST. And again, I can enable radiation or add a heat source if I want to, which is not the case here. Okay, so now we have our solids and fluids. Next we have our design domains. So the design domains are the volumes where ColdStream is allowed to modify the geometry. Here we have 3 heat producing components, so we want to put 3 small heat sinks on top of those. So I prepared 3 small subregions above each of the heat sources. The input now will be a subregion of type design. So I let ColdStream know I want to design something in this volume, And next, I specify what kind of cooling structures ColdStream can consider. If I'm looking at CNC milling, I can look at circular or diamond shape pins or rectangular fins. If I allow DPMS structures, I can consider any one of these 6. If I allow for die casting, I can again select circulars or pins or fins. And for sheet metal forming, you can consider circular or rectangular dimples. But in this case, I will select all options here, all 3D printing options, click on save, and now ColdStream will iterate through all 6 of those. Next, I specify my manufacturing settings, so letting ColdStream know what is my minimal feature size, what is my overhang angle of my machine, and support lengths. I will select this one for now, and I'll let ColdStream know in what direction I expect them to grow. So here it's again along the yellow arrow, but now in the positive direction. So I will select positive Y, and I have to let ColdStream know what material will be printed, which again will be our copper. And this is something that I can then repeat for design region 2. So here I'll again allow for all 6 DPMS structures, and now it's made of aluminum in this example. And for design region 1, I can do exactly the same. So now we have solids, fluids, and the design domain. The last thing that we have to add is what to optimize for. So currently ColdStream doesn't know anything about what it needs to do, and that's where the targets come in. At the bottom of every entity there is an add target button, and depending on where you add a target, the options will be different. For example, here for the design domain, I can either maximize the weight, so make it as heavy as possible, or minimize the weight, make it as light as possible. And for every objective, of course, you have the equivalent constraint. If I have a maximum weight constraint, I can put a maximum relative volume constraint, or if I have a minimum weight constraint, I can put a minimum relative volume constraint. But in this case, we don't care about the weight. Make it as heavy as possible if ColdStream deems it necessary. We mainly want to focus on the heat sources, and here, of course, I want to maximize heat exchange efficiency. So I will put a temperature minimization objective, and I will repeat that for the other ones. Oh, yes. And then lastly, to chip 3, also put a temperature minimization objective. So ColdStream does support multi-objective. By default, it will put a weight equal to 1, the highest value. If one chip is more important than the other one, I can lower or increase the weight depending on the priority that I select. The sum doesn't have to add up to 1. So if I put 1, 1, and 1, that's all perfectly fine. Okay, that's it. I hope you agree with me that it's fairly intuitive, fairly easy, and if you train a bit, as I mentioned, in a couple of minutes, you will complete all that input. So what you can now do, I have to fill in a bit more information, but let's say if it were all filled in, I can then submit the case, and ColdStream will start computing for me. We don't have to wait for the results to complete, so I can go straight to a case that is finished. When a case is running, you will get intermediate data points. In this case, ColdStream out with 99 different iterations, and in the design evolution graph, I can have a look at each and every one of those iterations. So in the overall design performance graph, the first graph, on the x-axis I have the iteration counter, and that should also be seen as a time step. ColdStream will first output the first iteration, then the second one, and so on and so on. And on the y-axis you have the performance value. A bit counterintuitive. The lower the value, the better. It's a bit counterintuitive, but it's a default within optimization. The lower the value, the better. And I'll come back to what this value actually means a bit later on. And then, yeah, for every iteration there's a single dot, and depending on the color of the dot, that means something differently. For example, here, if I have a red dot, it means the design is infeasible. Let's say if I put a maximum weight constraint and the iteration in the design exceeds at least one constraint, it will be marked as infeasible. If it's blue, it means it's a feasible design, but at this stage, it isn't the best one. And if it's green, it means at this stage, it is the best design. So here, iteration 1, it was feasible. At that point, it was the only design that was available, so that's green. Iteration 2 is again feasible. It improved upon the previous iteration, on the previous green design, so that's also green. 3 and 4 are feasible, but are worse than iteration 2, so they remain blue, and so on and so on. So then you know that, for this example, iteration 96 is the best design out of all of them. And if you scroll down, we can then have a look at what designs ColdStream added within the design domains. So here in design region 1, we have a gyroid structure with these dimensions. In design region 2, I have a split P design with quite thin structures, so here with these dimensions. And in design region 3, I have again a split P, but now with bigger walls. And of course, if you want to download those designs, they are available in this example in STL or 3MF format. And if you scroll down even further, then you see the individual performance values of all 3 targets. So as you remember, we put temperature minimization objectives on each of the chips. So here you see how those objectives behave throughout the optimization process. Basically, the weighted sum of all three graphs will give me my first graph. So the performance value that you see here is the weighted sum of each of your objectives. Okay, let's move on. Let's go back to the slide deck. Here in this video, it's a bit of an illustration of where that electronics box is placed, and you also see how the designs basically how the designs evolve through the optimization process. Yes, that is towards the end of the webinar. If I have a look at the timing, I think we have to skip the Q&A session, otherwise I'll extend beyond the 30-minute mark, so my apologies for this, but keep on asking questions, the moderators are still following along. If you want to try ColdStream for your own, if you want to try ColdStream to see how it behaves on your applications, feel free to contact the team. You can get in contact with us by either emailing to info@diabatix.com or just ringing this phone number. Or if you want to try, if you want to see ColdStream and experience what the look and feel is, there is a Try Now account where you see some of our finished demos, and you can request access to it via this link. Okay, that brings me towards the end of our presentation. So thank you all very much for your time. Thank you all for your questions, and I hope to see you in the near future. Bye bye.